Today, I will talk about a new type of semi-targeted attack on federated learning based on backward arrow analysis. My name is Yuwei. I'm a PhD student at the University of Tokyo. For today's talk, I will try to discuss model poisoning attack on federated learning by convincing you the targeted choice in traditional attack methods. I introduce a new semi-targeted attack. It will include two methods, the attacking distance aware attack and the fast layer gradient method. First, let's begin with several samples of poisoning attack on neural nets. In multi-class classification, an adversary aims to compromise the system such that instances from a specific class will be misclassified. For example, in the real world, a self-driving car that recognizes a stop sign could be compromised such that the prediction of the stop sign will be wrong. An attacker wants to bypass the facial recognition system such that the criminal will be recognized as an authorized user. Such misclassifying problem can happen in the progress of building AI, which is okay. However, it's usually not applicable in the real world. Ideally, the attacker would have the access to the full data used in the training. However, in reality, usually there's a limited prior knowledge about the data distribution of the other clients in the federated learning. In this study, we consider a more realistic setting where a compromised edge device is used as a backdoor to introduce the system. Namely, the federated learning we consider in this study. In the federated learning, there are different clients. Each client has its own datasets and local model. Moreover, each client cannot share data with others, mainly due to data confidentiality. Federated learning aims to train a global model by leveraging learned local models of clients by model aggregation. The goal of an adversary that mounts poisoning attack on federated learning is to produce a poisoned local model update, such that after model aggregation, particular input will trigger misclassification of the global model. Moreover, these attacks are usually either untargeted or targeted. The goal of the untargeted attacks is to degrade a classifier's performance in general. By contrast, the targeted attack aims to trigger the misclassification of a specified class. We mainly focus on the targeted attack in this research. In particular, label flipping is one type of poisoning attack where a set of data's labels are randomly flipped to a different class for malicious model training. Let's say we want to poison the source class of the bird's images by either relabeling it to the class of airplane or deer. We can expect a different attacking performance. For that reason, our assumption is that an attack can become less effective when shifting to a different target class. The adversary's performance can usually vary from case to case with different target classes considered. Its robustness to different attacking cases is barely guaranteed. An attack based on a less effective target class would require a longer convergence time to achieve the same attack performance. Furthermore, a longer convergence time allows an applied defense strategy to more easily discover the attack. Intuitively, if the adversary can choose the most effective target, a poisoning attack will be greatly enhanced. Therefore, we focus on a novel type of poisoning attack where the motivation of the attacker is avoiding being recognized as a specified class. We call the class of samples used for attacks the source class CS, and the final class which a sample is modified to the target class CT. Suppose the attacker is assigned a class, namely the source class, and the aim of the adversary is to poison the classifier so that samples with the source class are recognized as a specified class other than the source class. We call this type of attack semi-targeted model poisoning attack. Different from the targeted attack, the adversary can freely choose a target class so that the attack performance is maximized in the semi-targeted attack. The challenge here is how to find the target class optimized for the assigned source class, resulting in the best attack performance. In reality, finding the optimized C star is usually not tractable since it's a black box setting. But first, if the feature distribution is a white box setting to the attacker, for example, the distribution of different clients follow an independent and identically distributed RID manner, can we find such optimized, say, target class to mount the attack? The answer is yes. We can measure the attacking distance by using the Euclidean distance between the latent fixture distribution of two classes. A small attacking distance AD offers a small malicious update to compromise the source class, which is related to the feature collision ideas. A larger chance of surviving the model aggregation as a result. On the other hand, the attack we just discussed is limited to the ID setting. So we want to consider a more realistic setting. Since in real life, it's usually difficult and even impossible for the adversary to know the entire feature space in the federated learning, and the distribution of clients will be much more different between each other. In other words, it's unfeasible to extract the latent fixture representations of all the classes and measure the attacking distance, since only the partial class representations are available to the adversary. To solve this problem of the partial knowledge about client data distributions, we propose the fast layer gradient method that employs the update scale to estimate the distance between the source class and the assigned class. Simple patterns such as lines, curves activate the neurons in the shallow layer, while more complex vectors in the deeper layer. In particular, if the update scale in the higher layer is larger, when assigning a specific class, the attacking is assumed also stronger. By contrast, if the ground truth label is assigned, the update scale is supposed to be near zero. To mount the attack, the adversary first inputs the source class samples into the local model and feed forward propagates to obtain the output of the model. The loss between the prediction and the assigned label is computed based on the cross entropy loss and back propagated to compute the update gradients. Then we take the derivative with respect to the weight parameters of the last fully connected layer. Then from the gradient norm, we can measure the expected attacking distance by comparing the different updates scale, so that we can find an optimized target class by choosing the minimum, by choosing the target with a minimum distance to the source class. If a compromised client is selected by the server to perform the federated learning, it will download the latest global model to replace its local model. Then train the model LADV with the poisoned samples, and corrupt the global model by iteratively submitting the malicious updates to the server. This malicious model updates, however, usually is prone to producing large norms compared with other legitimate updates, rendering easier discovery by the defense method as shown in this graph. The box in the graph shows the norms of benign updates. The red line shows the norm of malicious updates. The green line, which is the boundary suggested by the defense method, will drop any updates that has a norm above this threshold. As we can see, the malicious updates will be removed by the defense. On the other hand, from the perspective of the attacker, since the boundary is set so that regular updates are not rejected, attacker might try to bypass the defense using the trend scale method. First, the adversary modifies the scale of the malicious model update so that it's upper bounded by the threshold Q. As shown in the graph, the norms of malicious updated are bounded by the threshold. They will not be removed by the defense method. The problem here is how to estimate the threshold. The attacker can first adopt several compromised clients to perform the benign, the normal training, and adopt the average norm of the collected updates from the different clients as the lower bound of the threshold Q. For the experiments, we adopted 100 clients in the federated learning settings and mounted the attack after the global model converged so that we could better measure the attacking distance in the feature space. We make sure that adversary had only a small possibility of being selected in the federated learning every round. And we also employed the different attacking frequency by varying the ratio of the compromised clients to the total clients in the systems. To measure the performance of the proposed methods, we're using two different metrics. The attacking task accuracy evaluates the success rate of an attack. On the other hand, the main task accuracy evaluates the success rate of the classifier for samples that are not from the source class. For both metrics, a higher score means the model performs better. Let's look at some results using the MNIST, Fashion MNIST, and the Federated datasets. These datasets pose different degrees of difficulty for perturbating the system. The table shows the performance comparison among the ADA with foreknowledge, the ADA4, the label flipping attack, the LF, and the trend scale method, abbreviated TS, when using different attacking frequency to mount the attack. The proposed methods as shown in the table show the best performance. The proposed ADA method succeeded in increasing the attack performance by 1.8 times, when the attacking frequency is as low as 0.01. In this graph, I show the distance visualization between different classes from the Federated datasets. For example, give the bird image class, the faster layer method shows the deer class has the smallest attacking distance, whereas the track class has the largest attacking distance. And we also can find that the images of animals are similar, akin to each other. The images of airplane somehow also show high similarity to the images of birds, which is reasonable. This graph shows attacking distance measurements in the two different settings of attackers' prior knowledge. As we can see, we successfully align the different classes to mount the attack. To conclude, the goal of this work is to introduce this new type of semi-targeted poisoning attack and review the risk. We introduced two effective methods for the white box and black box setting, respectively. In the more challenging and realistic black box setting, we performed the backward arrow analysis to measure the attacking distance between different classes. This work can be extended to generate semi-targeted backdoors based on the reviewed attacking distance. We can also study effective defense method against the proposed attack in the future. Finally, this work aims to raise awarenesses of the inherent risk of the poisoning attacks to the federated learning.